Wait. Hello. All right. So welcome back to DSP. And so we will start from where we were left last week. So last week we introduced, near the end, we introduced a new notion of Fourier transform that by the name DTFT, discrete time Fourier transform. And the definition is just shown right there, which I'll just copy on the board. We have on the right-hand side, we have a sum of any given signal, and we would multiply signal with e to the minus j omega n. And now the result becomes a function of what? A function of omega, basically. So it's a spectrum. Yeah. So last time I also suggested, I pointed to you that somehow there's some reason that will be clearer later. There's a reason why the textbook suggests that we use this notation. The notation inside here we put e to the j omega. Okay, so but we want to really emphasize that the result is a function of omega, which is a function of frequency, and it's called the spectrum, and that defines the discrete time Fourier transform, or DTFT. Okay, so far so good. So here the idea really is a projection, if you will. It's a projection from the time domain to the frequency domain, or is you create a representation, a signal, a way to represent your signal. There are a few words that you may encounter later. It's a representation. Okay, yeah. So that's a direction from time to frequency domain, like that. But we can also go backward. But given any spectral representation, you can get back to the time domain by applying what we call an inverse transform. Okay, so last time near the end, we also sort of proved to you that the inverse transform, if we just take the spectrum on the right-hand side and then try to collect all the terms through an integral with respect to omega. Okay, and the range, the limit of the integral is from -pi to pi. And that basically gets you back your signal in the time domain, except that there is a normalization factor of 1/2 pi. Okay, so last time you just recall we made some simple derivation involving change of singular order of summation and integral. 换顺序啊. So that kind of derivation, of course, you can do that. But I want to share with you my way of looking at this equation, this equality, 这个等式啊, this equality. How do I look at it? So the way I look at it is that given a spectrum, right? So as I said, spectrum is a representation telling us how much of a signal we have at every frequency, right? At every frequency, we have a component, we have a magnitude. So now, of course, at every frequency, we have a magnitude and phase, of course. Then we multiply with the small wave component. E to the j omega n itself by itself is a periodic signal. Complex value, but it's periodic with a frequency omega, right? So of course, if we collect everything through an integral, we get back the signal. So sometimes this operation can be referred to as synthesis. You get a spectrum that's sort of like analysis. We analyze the signal by looking at or by examining its spectrum. So that's an analysis. This is a 分析, spectral analysis. But once you get spectrum, you can also synthesize, 再把它合成回来, or more fancy term, if you will, generation. You generate a signal by collecting the spectral component and adding everything back together. Analysis and synthesis, analysis and generation. 生成 is more fancy, but traditionally we use the word synthesis, 合成, synthesize the signal by collecting all the spectral component. So that's the way I look at the forward transform as well as the inverse transform of DTFT. So later, today's agenda, we will continue to talk about properties of DTFT. Okay, so that's the first thing, and I think we do have time to move on to the next lecture. So let me just briefly touch on today's agenda. 隔壁没有开投影啊。Can you go help? So now, thank you for Any question? 好，那 please take a break until the problem is fixed. 我去隔壁，let me go to the next room. Eh, 那可能对不起，那就麻烦你们到隔壁去。哦，那还有什么？有直播有开吗？直播有开是不是？那可能会 delay 个大概10秒之类的哈。好。好，那赶快敲一下助教来啊！对。YouTube 的 link 在。 好，那我再那个给你们2分钟时间啊。好，哎呀。Okay, so fortunately the lecture is also being streamed through YouTube. So now I ask the next room people in the next room to log into YouTube. Sorry for that, this technical problem. Right. So anyway, forward transform, inverse transform. Yeah, and now I'm missing my projection. Wait, good. All right. So today's agenda. So we will continue to talk about properties, important properties of DTFT. And then maybe in the next hour, second hour, move on to lecture 3. Lecture 3 is about quantization. Quantization. Basically, we need to discuss how we represent our signals so that they can go through computation, right? Digital computation. So we'll move on to that topic maybe in the second hour today, right? So far, so good? Okay, so if you're interested in a complete coverage, 完整版, if you're interested in the more complete coverage of all possible properties there in DTFT, please refer to a textbook. Okay, in textbook chapter 2, there are 2 sections dedicated to all the properties. But here I mentioned first, I would like to mention maybe 5 or 6 properties that I will be using a lot. Okay, that I'll be using a lot. So I'll introduce these properties first. So let me go. So let us go over them one by one. The first property is periodicity. Okay. So basically, if you take a closer look at the definition over there, you'll find that you'll soon realize that if we just evaluate the spectrum at a frequency plus 2 pi, the result is the same. That makes sense? If you evaluate the spectrum by replacing omega right here with omega plus 2 pi or 4 pi or 6 pi, the result will be the same because n are integers. Okay, so we need to, by now you should be familiar that here when we say discrete time signal in this convention, in our convention, 在我们的习惯, even our convention n is integer. So therefore, omega, if you evaluate the spectrum at omega plus 2 pi, the result is the same. That is to say that the spectrum in the frequency domain is periodic. Okay? Or if you will, sometimes I use a more sloppy representation. Let's just remember, if you evaluate the spectrum at omega plus 2 pi, just without, just while maintaining clarity, so it should be clear that in this notation, I'm just using a simpler notation that the meaning, the spectrum becomes periodic, okay, according to our definition. That's a very basic property, okay? So that's a very basic property. So if you, let me move back to over there. So the first property, well, can we set this to, so that it never sleeps? This is not my computer. Let me set it so it doesn't sleep. So it doesn't sleep. Where should I go? Maybe here. Is it here? Is it here? No. 不对。怎么样能够让不要 sleep? Is it 显示器? Is it? Anyway, so maybe I'm encouraged to walk back and forth more. So to touch the screen every 30 seconds so it doesn't sleep. Periodicity. So yeah. So what it actually means is that when you draw the spectrum, let's say again to just depict if our spectrum is like a triangle right there in the baseband, if this is omega, then at omega equals 2 pi, everything repeats. Okay, seriously, that's as simple as that. As a simple matter of fact, the spectrum is periodic for any signal you can think of. Okay, and same thing for the negative frequency side. We also get another copy. The spectrum itself repeats indefinitely every 2 pi. Spectrum becomes periodic. So therefore, now keep in mind that when you draw a spectrum, we don't need to show these other places, right? Because we know that it's a basic property that the spectrum is periodic. So every time you draw spectrum, you can feel free to usually only show the middle part, only show from minus pi to pi. That will be enough. That suffices. That will be enough. Okay? You don't need to show extra range because we know the spectrum is periodic. Okay, so that's kind of the application. That's the implication. This is how, yeah. So that's that. So the second property is about symmetry. Okay, so again, just like the continuous time Fourier transform, when our signal is real in the time domain, for all samples, then the spectrum has this symmetry. Okay? So that is to say, if we evaluate the spectrum at minus omega, that's the way we read it. Okay? If we evaluate the spectrum at minus omega, the result is going to be complex conjugated. Complex conjugate, 共轭复数, right? So how do we show that? Okay, so property number 2, let's do a quick check. Okay, and let's try. If you can work it out by yourself, that'll be cool too. But let's say now, how do we check this? When we evaluate our spectrum at minus omega, that means we still perform this summation, but then evaluate according to definition minus j, and we evaluate everything at minus omega, right? So that's the meaning of going to the negative frequency side to evaluate our spectrum at minus omega. So we plug in minus omega right here. That clear, right? And so that becomes so x obviously, to move one step further, it obviously becomes this, right? It obviously becomes this. And so now, let's try to, therefore, if you take a complex conjugate on both sides of the equation, take the complex conjugate on both sides of the equation, we have x complex conjugate e that. Just copy everything here, and we have a big parenthesis, complex conjugate. Just take the conjugate on both sides of the equation, right? But then the next step, what is the next step? Can we move the complex conjugate inside the summation? Of course, yeah, complex conjugate works that way. And so we can move the complex conjugate inside the summation E minus j omega n. But then, what happens? We begin with the assumption, a very reasonable assumption that our signals are real in time. We begin with this assumption, right? So therefore, what is x conjugate? X is real, therefore x conjugate is itself. So therefore, this is itself, and we copy the next term right there, and we soon realize that this is what? This is our definition of the Fourier transform, evaluated on the positive frequency side. So the two of them becomes mutually conjugated. they become complex conjugate, just because our signal is real. So the two of them are complex conjugates. 互为共二复数, they are complex conjugate. So far so good? Yeah? So that's the second property. Yeah. Now moving on to the third property, if you take a look first, while I'm erasing the board, if you take a look at the third property, you probably can find that there is a sort of a similarity. 有点相似性啊. There is some kind of similarity in the property number 2 and property number 3, right? So now it's like property number 2 tells you that if real in one domain, then symmetric in the other domain, right? So now the third property is that, oh, okay, now symmetry in one domain, real in the other domain. So that's the similarity I was talking about. You can try to compare. Do we all see that? Real, being real, valued in one domain, implies there's a symmetry in the other domain. Okay? Be real in time or be real in frequency. So let's, by the way, you can, of course, tell that everything is double arrow, right? Everything is double arrow there. So it's if and only if. If I really want to emphasize that. I should say that X is real if and only if that, or X is, wait. Oh, yes, if and only if. Everything is if and only if, okay? But anyway, so let's take a look at the third property. Take a look at the third property. If X is real by our convention, okay, by our habit, we assume that our signal is real in time, and our signal has this property, this symmetry property in the time domain. In addition of being real, it also has a symmetry in the time domain. Then how do we show? The spectrum become real valued, no longer complex, only a real part. Okay, how do we show that? So again, we begin just with our definition. Our definition, just write it down, summing over all n e to the minus j omega n. Okay, so that's a good old definition. And our end result, we want to show that the spectrum is real valued. There's no imaginary part. How do we do that? Applying the assumption, applying this assumption. How do we do that? So my suggestion is to break the summation into 3 parts. Okay, we are going to break the summation, the infinite, into 3 parts. The first part is the negative time part. E minus j omega n. And the second part is the plus time part from 1 to infinity xn e minus j omega n. And there's a third term. What is the third term? The third term, what's the missing term? E equals to 0, right? Yeah, so the third term is n equals to 0, only one term, no summation. So x0, e minus j omega 0, right? So immediately we have a progress. This is exactly 1, and x, because x is real, so this component is already real. We know that. So we can leave that alone. Okay, we know that the third one, this component is a real number. But how about here? So then now we need to somehow combine these 2 terms. So I would suggest let's try to change the dummy variable. Let's try to change the dummy variable. Now, change the dummy variable. So the first term becomes, we define m equals to minus n. Let's try that, okay? And change the w variable right there. So if we do that, then this summation becomes m now goes from the range 1 to infinity, right? And if m is minus n, then n is minus m, so this is x minus x of minus m, right? And then how about right here? We have e minus j omega minus m. And plus, that term is already still there. We don't need to change it. xn e minus j omega n, and plus the last term is x0. We know that, yeah. So we still have 3 terms that we are making a little bit of progress, right? Can you see that we are making a little bit of progress? 有点点进展啊. So now how about here? Now we are ready to combine these 2 terms. First of all, m is nothing but a dummy variable, right? So can you allow me to change its name back to n? It's a dummy variable, right? 就像你改名字改叫鲑鱼嘛，还可以改回来啊。Change the name back to n, okay? Yeah. No more salmon. Now, rename it n. Rename it n. Oh no, the minus sign is still there, okay? And just rename it n plus plus, okay? Just by the way. So now what do you, now we become, but what's next? Remember that we have the assumption, we're discussing symmetry. So here in this property, we assume symmetry to begin with. We assume our signal has symmetry in time. That's the assumption, okay? So with this assumption, what do we say? With this assumption, now we know that this term equals to xn because of the assumed symmetry, 假设的对称性啊. Because there is symmetry that we assume. Then now, we are more ready. We become ready to combine the 2 summations, right? Now we become ready to combine the 2 summations. Can we see that? How do we do that? So now we become ready to combine summation. Now the summation goes from 1 to infinity, and we on both summation we do have this term x of n, so we can just put it in. And then the only difference between the 2 summations is that now we have in here we have e to the plus something, and right there we have e to the minus that thing, right? So now we have e to the plus j omega n plus e to the minus j omega n, and let's also not forget the last term. Still, we copy it right here. Okay. So now what happens? What happens? Isn't this also real? Yeah. Because now we see that combining these 2 terms, we know this is 2 cosine omega n. Right? So now, finally, we're happy, okay? X is assumed to, our signal is real. 2 cosine omega n is real. We sum them up, everything is real, plus a real number, everything is real. We have completed our check, okay? Our verification on property number 3. Okay, we have completed our verification of property number 3 if our signal has a symmetry in time, then we have the spectrum becomes real valued. Okay, in this special case. Let's shut down one more time. Okay, so maybe let's take a 2-minute break while we try to fix this. Okay, yeah. 陈飞可不可以帮忙一下？这个要设哪里啊？是在哪边做设定？萤幕使用时间吗？应该不是，看那个系统设定那边能不能设那个电池 battery。是电池啊？对。哎。然后往下滑，看会不会有？不太像啊。没有。对，不是电池。 So any suggestion? Does anybody know how to ask it not to sleep? 怎样能够让它不要睡？好像也不是这里。
你知道是哪一个？
跟那个无关，哎，怎么？哦，对对对，好，谢谢谢谢，反正1小时啊 ，OK，good， 好好好，非常好。OK，yeah，thank you TAs，yeah，let's all right, we figure it out. That's good, yeah. Okay, any questions so far? Yeah, regarding the properties, please show up. Yeah. Thank you, properties, please come back to us. We miss you. It's great. What happened? No signal. 线有啊 ，Yeah. 应该有，他好像有感测到。好，谢谢谢谢。Oh, good. Okay, so hopefully this will last for 1 hour. Okay, so there's a symmetry in time which leads to the result of spectrum being real. So if you're interested, there's another property, very similar property that I don't list on this slide. Another property stating that there's a condition, another kind of symmetry, which will lead to the result that the spectrum become purely imaginary. 变成纯虚部 purely imaginary. There's another symmetry. Yeah. So basically, even function, odd function. That's sort of symmetry. But the spirit is there. Symmetry in one domain, real or purely imaginary in the other domain. So that always applies to all sorts of Fourier transform. Okay. But anyway, so we focus on the third property. We'll be using it later in this semester somewhere. So I promise. Yeah. The third property is also very important. So let's move on to this next property of basically shifting in time. Yeah, shifting in time. So this property goes that if we shift the signal to the right by m samples, shifting it to the right, delay, if we apply a delay of the signal, okay? If y is x delayed by m samples, where m is also an integer, right? Now this happens a lot, right? You delay the signal by a few samples, why not, right? And then again, we ask what will happen in the frequency domain? What will happen in the frequency domain is a phase factor. So by shifting the signal in time by m samples to the right, on the frequency domain, the spectrum becomes, there's an extra phase term that shows it right here, okay? We have an extra, the original spectrum is going to be multiplied with this e to the minus jm part. That's a result, okay? That's a result. So I will leave this as an exercise for you, okay? It's rather straightforward to show that this is true, okay? This is true. But let me just copy this. Fourth property, if y is x delayed by m samples, by shifting to the right by m samples, then the spectrum of y is basically the same as the spectrum of X, except that we multiply with a phase. Sometimes people say this is a linear phase term. Linear phase term. And the idea, the reason, okay, so if we just contemplate on this result, before we formally prove it, okay, which is left as an exercise, I often like to invite you to contemplate on any property, any theorem, contemplate on the result. Contemplate 就是查看，然后并且叫什么？ to contemplate 啊，去开始联想啊。Let's contemplate. Look at this result. How do we interpret it? Is there any insight? By looking at this result, this is mathematically true result, but what's the insight? What's the insight? What's the insight? Anybody? If you have learned it, if you haven't learned it, anybody has an insight? Does everybody have anybody has an insight? 这位同学，你说说看啊 ，Sam， 神学有我导生啊，any insight？
怎么理解啊？
对，
就是把那个y 线看成那个 y 线看成一堆那个什么旋转的那个一的那个东西。
So we regard y as something that's rotating around. Yeah. Yeah. Yeah, it will take the time. Yeah, 把时间 what? Yeah. What do we do to the time? 把时间什么？
把时间平移的话，
对。
它旋转的起始点变不一样。然后对应到那边。有
变多不一样的。
对应到那边就是加上一个旋转。
Yeah. So that's a very good idea, very good insight. So basically, we are talking about. So let me try to interpret what you say. So basically, please note that here we have complex numbers, right? Complex numbers, multiplication, complex in general, right? So when we multiply two complex numbers on the right-hand side, what happens? When we multiply two complex numbers, what happens? The magnitude multiplied by the phase adds, right? Yeah. So that is to say, the spectrum, if you take the phase spectrum, if you take the phase spectrum, then that equals to the phase spectrum of X. Now, plus the phase of e to the minus j omega n, which is by default, this extra term by default is what's right here on the exponent. 指数的部分 exponent, right? So we just simply say minus m omega. Yeah. So what does that mean? That means what is frequency? Frequency tells us how fast the phase repeats itself, right? So therefore, when we move the phase, the signal in time by m samples, it introduces so much phase shift. That's kind of insight. At every frequency. If we just move the time in m by m sample, then every frequency has a phase delay. By how much? By m times that frequency. So that's why we call this a linear phase term. Okay? So that's a very important and basic concept which is mathematically true and not hard to interpret. Okay? So if it just I'm pretty sure that just by some contemplation you can create your own way to understand this mathematical property. Linear phase term, okay? When we introduce a delay in the time domain, when we introduce a delay in the time domain, then that leads to some phase delay in the frequency domain for every frequency. And the phase shift is different, and it's a linear phase shift. It's proportional to the frequency. M is the time, M being the time. Okay? Is it making sense? Things are making sense so far? Regarding how we look at this property, is it making sense? Yes? It's making some sense, right? Why do we need for property? It turns out that we do need property 4 to prove property 5, okay? Property 5 is the most famous one that we are glad to cover today. So convolution. So now let's read. Let's read all the text first. Okay. So if we define the convolution of two signals, here we say x and h, both of them are signals in time. And this operation is to just somehow do something when you have two signals, h and x, namely. So we define this as their convolution. The result is also a signal in time. When we convolve a signal with the other, the result is also a signal. The output is a signal in time. Okay? Convolution happens in time domain. And the definition is by, if we take a closer look, the result is signal, but then we sum over all k. Sum over all k. And here we have x. K goes in the positive direction, but here k goes in the reverse direction. Okay, so in this way, you can sort of think of h as convolution as if we are flipping a signal in the time domain and then perform inner product with the other signal, and then we flip and shift. After flipping, we just gradually shift the signal by n samples and then sum the calculate the inner product. The result is another signal. It's called convolution. And for those of you that have been exposed to this concept, convolution in Chinese is often translated as what? What's the translation? Chinese translation for convolution? 卷积啊，哦，好，谢谢啊。Convolution. Wait. This computer is being naughty. Didn't we already say convolution translation is 卷是吧？花卷的卷还是书卷奖的卷 ？Seriously 啊，我不要讲书卷奖，要讲什么？内卷的卷，卷积。书卷奖的绩，卷成绩的绩，好难过，好卷哦。I call it 折积啊，yeah， 折积 or yeah。The word 折 is just emphasizes on this you flip one signal to let the time go backward, to let the time index going backward. Anyway, this is a pretty straightforward mathematical definition, and soon you can realize, convince yourself that this convolution is what? Commutative. 具有交换性。Convolution is like multiplication or addition, like 乘法跟加法。Convolution is commutative, 具有可交换性 commutativity. So just note that x convolves h by this definition equals to h convolves x. Doesn't matter. You can change because this binary operation is commutative. It's commutativity. Commutativity. There's a commutativity in this definition, convolution. But then, let's continue reading. Okay, so if convolution is defined such a way, then, indeed, I do have this note. Note that it's commutative for arbitrary sequences x and h. But then, also in the frequency domain, beautifully, we have the spectrum becomes the product of the two spectrums. The spectrum of convolution becomes the product of the two spectrums. And of course, product is also commutative. So nothing is being tricky. There's no trick. Okay? Commutative in the frequency domain, commutative in the time domain. But now, important thing is that we change the convolution in time into simply doing a product in the frequency domain. For all frequency, okay, for all frequency, we say between minus pi and pi because the spectrums are always periodic, right? So we can simply say that. And this property, the property is that when you go to the frequency domain, this property of the spectrum being the product of x and h, this property is called the convolution theorem. Convolution theorem. Convolution in time product in the frequency, multiplication in frequency. So now I would like to take some time for us to all work out how to derive the convolution, how to verify that the convolution theorem. Yeah, so that's what we are going to do next, probably before the break. All right, so how do we prove that if y of n is x convolved with h, then also in fact only if then y, the spectrum is, put a question mark here, you're serious? Spectrum becomes the product. How do we show this? How do we show this? Okay, how do we show this? Okay, so which direction should I go? So now, let's check. Okay. So I intentionally left the next page blank, so you can write it on the page if you have your iPad. But now we are, what if yn is summation over all k, x k, h n minus k. So that's a definition of convolution. Now we're interested in evaluating its Fourier transform, right? So what is y's Fourier transform? By definition, y's Fourier transform is summation y, and which is y look like this inside. So this is y of n, right? This is y of n. And then by the definition, the Fourier transform of y of n is an inner product, right? What do we do here? So we apply e to the minus j omega n. So that's according to the definition. This is how we just basically we just substitute yn with this summation because y is x convolved with h. So far so good? So far it's just a simple substitution. 只是一个替换而已啊, a simple substitution. And then what's next? What's the hint? When we see two summations, what do we try to do? This will appear over and over, right? When we see two summations, just without your blink of your eyes, 不要眨一个眼睛啊, immediately, 立马, 马上啊, immediately we change the order of summation. Not the most mathematical rigorous thing to do, but in most cases, in 99.99%, that will lead to that's the correct direction. So let's try. Let me just be humbly just say we try. We try, right? No offense. You can always try something to see if things work. Let's try to change the order of summation. Let k go outside and n go inside, right? So if you let k go outside, then anything that does not depend on n can move to the outside temporarily. 暂时把它放外面啊. Then n still goes in. So anything that depends on n needs to show up right here. N minus k e minus j omega n. So that now n goes inside, right? N goes inside. So far so good? Just changing the order. Just changing the order. So can anybody suggest what can happen next? What property do we apply? Isn't this, aren't we ready to apply that property over there? Now, if you look closer, what is this? This is the Fourier transform of h, but shifted by n samples, by k samples. K's outside, right? This is just a shift. So by applying shift theorem, so we will apply shift theorem. By applying shift theorem, immediately we notice that this is the result is going to be h, but with a linear phase term, right? With a linear phase term. Now, what is that linear phase term? The linear phase term is e to the minus j omega. Let me be clear, and this shift right there. Yeah, linear phase term with k samples. That's a shift theorem that we have just applied. Yeah. and then we will copy everything else. And we copy everything else, right? And we copy everything else, and we are basically done. We're basically done. 基本上就结束了啊。We're basically done because now this term does not depend on k, right? So we can put a parenthesis, a big parenthesis around the summation. And what is this? This is nothing but x, the spectrum of x. And thus we have arrived our conclusion that indeed, when we convolve two signals in time, that leads to a multiplication in the frequency domain. Convolution in time domain, multiplication in the frequency domain. Okay, so I think we still have a few minutes. We still have a few minutes. I think we can take a break. Okay, let's take a break of 10 minutes and get back around 2:18 on my clock. Right? Yeah, take a break of 10 minutes before we move on to the next theorem. Okay, so I'm going to resume my lecture in about 1 minute. So 大概1分钟后我再开始讲啊。Okay, so before we move on to the next property or next theorem, I'd like to take this time to mention the application scenario of convolution theorem. Okay? In what scenario do we apply the convolution theorem? The most important scenario is later in this course, we'll encounter a kind of system that's called LTI, which we'll cover. That LTI stands for 3 words, linear time invariant. Okay, so it's kind of LTI system. For any input x of n from the left, you obtain the output y equals to h x of n convolve with h of n. So in other words, such kind of system is, we say, is characterized by h of n. What that is called is impulse response. So there's a class of systems which is characterized by their impulse response. In the sense that for any signal that comes into the system as an input from the left, the system processes it by convolving that input with an impulse response. So there's a large class of LTI systems that can be characterized this way. Okay? The way it processes the signal is to convolve it with a kernel called impulse response. Right? So in this case, by applying the convolution theorem, it's more natural or easier to discuss what's going on in the frequency domain. Why? Because now, if you just take the Fourier transform, take a DTFT now, and talk about the spectrum right there as the input, then what it does, if we also take the Fourier transform, then the output, the spectrum of your output is simply the input spectrum multiplied with frequency response. The Fourier transform of impulse response is called, or can be regarded as, a frequency response. Frequency response of the system, which gives rise to a gain, a magnitude, and the phase. Okay? So further, you can talk about the magnitude of your frequency response, and the meaning is gain. It tells you how much gain does the system give to your signal if the signal's frequency is at omega. So gain is a function of omega. For those of you who have taken microelectronics 电子学，应该熟悉, you should be familiar with the idea. Gain, magnitude response. Now you have a system, a circuit or of some sort, that's in analog. But in digital, in discrete time, we have a very similar situation. Okay? We can have a linear time invariant system which gives you a gain as a function of frequency. Maybe it's a low pass, it's high pass, and so on. It tells you how much the amplification the signal receives if its frequency is omega. Amplification, gain, amplification. And of course, gain can be smaller than 1, so that means attenuation. Right? Amplification or attenuation can be understood if you just analyze the impulse response in the frequency domain. Attenuation. 是衰减还是放大? Amplification or attenuation can be analyzed through Fourier analysis. So that's the main application in this course. We will just keep coming back to this notion. Okay? This is a context where the most important context 最重要的情境啊 the most important context in which we apply the convolution theorem. Yeah. Any comment? Yeah. All right. Okay, but let's just keep it this way for the moment, and let's move on to the next property. To share with you also a very interesting property by the name Parseval theorem. So this is a theorem. So what do we have? The theorem is about the energy. About the energy. But when we say energy, really, this is basically kind of a mathematical course. So energy, when we say energy, like in the physical world, energy or power, energy is the time integration of power, right? 功率的时间积分是能量嘛 So energy is kind of to sum up the power in time or to take the integral. So therefore, on the left of this equation, on the left-hand side of this equality, we are summing the square, the magnitude square of our signal in time. Okay, on the left-hand side, that's a sum in the time domain. And on the right-hand side of this equality, we have an integral of the spectrum, or also the magnitude square. Yeah, the magnitude square in time, magnitude square in frequency. And they are essentially the same except for a factor of 1 over 2 pi. Okay? And this is a theorem, okay, called Parseval theorem. And of course, we need an extra assumption that we need to begin with the assumption that the signal, this summation converges. Right? If it diverges, then it makes no sense. Of course. Yeah. So there's an if. If the energy is finite, if you have a signal whose energy is finite, then that energy can also be calculated in the frequency domain by applying this integral. You can calculate the energy in the time domain, or you can calculate the energy in the frequency domain by integrating the magnitude spectrum square. Yeah. And that's a very fundamental property. Okay, that's a very fundamental property. Okay, so far so good? Energy can be calculated in the time domain or in the frequency domain. Again, let's contemplate. Okay, let's contemplate. Now we talk about Fourier transform. We already go from time domain to frequency domain. And there are symmetries and stuff, shift theorem, convolution theorem. But even without proving that this is true, okay, let's agree that this is true, then what do we learn? If this is true, what do we learn? So this is kind of a surprise. Even if we go to the frequency domain, then the way energy is the way energy is expressed, this expression is similar, right? Sum of square equals to integral of square. So there's a beauty in here. Yeah. Even when we go to the frequency domain, when we need to calculate the energy, the way we do it is pretty similar. Taking the sum of square in the time domain, taking the integral of square in the frequency domain. Okay? But more like profoundly, 比较更深入的, more profoundly, if you have learned linear algebra, okay, in the language, this is the point I want to share with you. In the language of linear algebra, we know that Fourier transform is a linear transformation. First of all, Fourier transform is a linear transformation you haven't been aware of. Linear transformation, right? So it's linear algebra, can be applied right here. So in the language of linear algebra, we say that Fourier transform is a kind of transform that preserves the norm. 它把那个 norm 范数给它是一个保持范数的这种变换。Let me say that again in English. Fourier transform preserve the norm. That's the kind of blank I want you to fill in. I want to share with you. Fourier transform preserve the, or if you want to elaborate, it preserves the L2 norm. So that to say, now you need to think of your signal as a vector in some sort of vector space. Because norm 是向量的长度. Norm is a kind of a length of the vector, right? So when we say norm, we are already thinking of our signal as if it belongs to a certain vector space. So let's just take this notion that if you try to think of all the possible signals in time domain to form a vector space. So in this vector space, of course, you can define Fourier transform is from your vector space to another space. Let's say W is a frequency domain, right? V is a time domain, W is a frequency domain. The Fourier transform is a linear transformation that goes from time domain V to frequency domain W, right? But then, basically, you're saying that the Fourier transform, if you take the norm of your signal now, it basically equals to your norm. Or I should say this, norm, norm square, Double bar means the norm, okay? Except that there's a factor of 2 pi. We can work it out. Okay, so there is a factor of 2 pi right here. It's not super important. Fourier transform preserves the norm. Okay. So this is kind of a point, a more profound. 比较 profound. What's the Chinese for profound? Profound. 比较 What's the Chinese for profound? Can anybody? Yeah, profound. This is a profound. Anyway, whatever it means. This is profound. Yeah. Profound. This is profound. We can find it out. Profound. The word. This is a profound property. I call it profound. Fourier transform preserves the norm because what is a norm? What is a norm? When you learn linear algebra, what do you take? How do you understand what is a norm? What is a norm? What is norm? I forgot. Good. Yeah. Can you suggest anybody who might remember what is norm? No, 你陷害同学. Who may remember what is norm? Can you make a suggestion? I don't know you all, so yeah. I don't know you at all, except my 导生, 专题生. 专题生来, what is norm? The unit length, yeah. So the norm, what is the norm of a vector? So if I have a vector in 3D, right? If I have a vector in 3D, right here, with projection and that, yeah. If I have a vector in 3D, what is its norm? Norm is nothing but the length, right? Thank you. Thank you. Thank you. So norm, so we are basically saying that this is a profound property in that we discover Fourier transform preserves the length of a vector. 1/2 pi, let's not worry, okay? For any vector, basically, it's not just a coincidence, not just for some signal, but all signal, any signal with a finite energy, then we realize that Fourier transform preserves the length if you take the signal as a vector in some sort of space. So does anybody know that for norm-preserving transformations, there is a term? Okay, yes, 请说. Unitary isomorphism. Yeah, unitary, thank you. Unitary transform. Wait, so check your linear algebra. Fourier transform basically is unitary in that it preserves the norm. But then back to 3D, can anybody give me an example of a 3D transformation which preserves the norm? I'm already giving you some hint. Anybody? Rotation, right? What kind of rotation? If I rotate my cup with water in it, if I rotate that, is that a unitary transform? Rigid body rotation. 钢体的，我翻译成中文，钢体旋转 ，right？ 钢体旋转 ，rigid body rotation preserves the known in that the distance are preserved. Distance between any two particles are not changed when we rotate a rigid body like this thing. When I rotate it, all the distance within my bar remain preserved, right? So I'm sharing with you that Fourier transform, when you look at Parseval theorem, is pretty profound because it tells us that Fourier transform in a way is like rigid body rotation. It's a rotation in an infinitely many dimensional space. 一个无限维度的一个钢体的旋转啊。It's like a rotation. And so there's a famous quote by the mathematician von Neumann. There's a quote by von Neumann. 冯纽曼啊。He's the founding father of many different fields, including computer science and quantum mechanics and stuff. But he has a book by the name Mathematical Foundation of Quantum Mechanics. 量子力学之数学原理啊。Mathematical Foundation for Quantum Mechanics. So in the opening, he was introducing Fourier transform, and he said something. He said Fourier transform. What is Fourier transform? Fourier transform is a unitary transform that diagonalizes the differential operator. Now, Fourier transform is a unitary transformation. For example, it's a unitary transformation that, it's very condensed, diagonalizes the differential operator. By von Neumann. 将微分算子对角化啊，将微分分子对角化。So, I will not test you on this, but I found it beautiful, so I cannot but share this with you. Fourier transform is useful basically because it makes our differential equation easier. Okay? 微分方程再用傅立叶转换来诠释是稍微is making it easier. Okay? Fourier transform is now by Parseval theorem, which we haven't proved. By Parseval theorem, I'm sharing with you that Fourier transform, but this version, DTFT. At least for DTFT, you can calculate the energy in time, or you can calculate the energy in frequency. And there's the only difference is 1/2 pi. Okay? And I'll leave this as a FUD question. Okay, maybe a few weeks later we'll come back to this. Okay? It can be proved rather. It's not the most straightforward, but it can be proved in about 1 page. But so for now, I want to share with you. This is a very profound, beautiful theorem right here. Okay? Any comment? 有没有哪边比较有疑惑的？It's profound, as I said. Okay, so now I just want to briefly mention a few more words for advanced reading. So this is optional. Okay, extended reading on what? On the topic of existence. Okay, so the message I want to deliver to you is that DTFT sometimes does not exist. Yeah, what do we mean? So not all signals have DTFT. And that's an important concept. Okay, we'll come back to that. But let me just try to mention, not all signals have DTFT. So we mean that sometimes that summation, sometimes it doesn't converge. That's what I mean. Yeah. For some signal, you can easily find a few signals that leads to divergence when you sum this up, when you attempt to calculate summation. Okay, so exists in this context. Exists means convergence. Fourier transform is defined through a summation, right? So you need to worry about in general. It's a valid concern. 是一个合理的一个忧虑哦。It's a valid concern. For some signals, maybe the summation does not converge. It can happen. Yeah, it can happen. And so, but for those signals that for which this sequence converges, then we say now Fourier transform exists. Okay, it's just a mathematical jargon. So we say that, let me just go through a few different notions. And the notion of existing actually can be different too. The first notion right here is that if the signal, if you take the sum of absolute value of the signal, if that converges, then that guarantees that Fourier transform exists. Okay, so let's just say another way to put it: if a signal converges absolutely, 绝对收敛, mathematical way to say it, if a signal converges absolutely, then that guarantees that the Fourier transform converges or it exists. So that's one notion of being existing, okay, of existing, 存在. That's one notion. But this turns out to is sufficient but not necessary. And the second notion, I'll just read it. Even if the signal does not converge absolutely, but then if the signal has a finite norm, sometimes this can happen too. For some kind of signals, the norm is there, but it's not absolutely summable. If the signal is not absolutely summable, but its norm, L2 norm exists, is finite, that can happen too, then we need to more carefully define the summation. Okay, then if we define your spectrum as the limit like that, if you let minus n and n approach infinity at equal speed, then this notion is well defined. Then it converges. Okay, then so again, this is just some extended reading you can find from the textbook. Okay, and that will conclude all I want to share with you so far for lecture number 2. All right, check it out if you're interested in such kind of discussions. It's there in the textbook. 好，那就先这样。好，so let's take a break of like 2 or 3 minutes. Yeah, let me switch over to my next lecture. 这个吗？好。哦，可是我这可能有动画的，也可以多播动画是啊。你来帮我操作一下啊。你没有 PowerPoint 的。好，可以有播放模式吗？应该是这个吧，这个播放吗？好。那还是用我的电脑好了。我想也许可能还是用我电脑。对。 crossed.绝望，每次都有问题。
是没有办法投影。
我只好再重新开。那个是 PowerPoint， 应该其实只要你登。 Hello. All right, so we're finally, sorry for the delay. So I'm delaying my presentation by m samples in time, right? Yeah, that's not funny. What's that?
就是因为现在没有网络连线，所以
嗯，
没有办法跑出来，
哦，是这样啊。
连到网。
哦，好好好好。其实没关系的，没关系啊，呀。但是你全荧幕啊，可以全荧幕吗？可以全荧幕吗？啊。哦，这样子啊。好，那再稍加油。We need the net internet. You know what? Let's just go through the slide quickly first. Then next week when we come back, we do a more detailed discussion, right? So just to give you a rough idea, so please bear with this smaller screen right here. So this lecture, let's begin. Next time I'll bring some guai into the classroom. Yeah, it's a lot of trouble. It's already the second week. Third lecture is down. So lecture 3, quantization and noise. Okay. So strictly speaking, of course, we're going to discuss quantization. How to represent a number, because discrete time signal are numbers, x of n. X, what is x? Is real number, right? But in general, a real number, any real number requires infinitely long fractional to represent, right? And for computation, we cannot afford that. We always need to talk about how we sacrifice, how to do quantization, how to round your value into the next level, how to perform in Chinese 45 rule. So quantization is about 45 rounding. And rounding inevitably, 无可避免, inevitably introduces some noise. So that's why quantization will always give you some noise, and we will discuss that in this lecture, right? So can we go to the next slide? TA, can you go to the next slide? Becomes a musical instrument. Yeah. So it's working. Oh yeah, thank you. Yeah. All right. Okay, so as I said, recall that we have an ideal continuous to discrete convergence where D stands for discrete time, right? And the mathematical expression goes this way. You have a continuous signal. If we just evaluate the signal at n integer multiple of a sampling period, then we get a sequence of numbers, but real numbers. The problem is those samples, all these real numbers need to be represented digitally before we can do any computation. So now, without further ado, this is a conceptual diagram for what we call A to D converter, analog to digital. Okay, and you can find it in the textbook too, Open and Schaefer in that textbook. So this is a direct copy from the textbook in which you see that your signal goes from the left into the C to D converter to become a real number, a sequence of real numbers, and then we quantize the sequence of real numbers. And the result is denoted as H hat. Okay? And then H hat, after quantization into finite levels, then we are ready to encode our numbers with some sort of binary representation, where B stands for binary, big B. Okay? Binary representation, 二进位的. So at this point, I also want to briefly mention a few parameters right here. So basically, we assume that before quantization, we need to determine what's the range of interest. Your signal may vary as a voltage, if it's an analog electrical signal, voltage. So we need to determine what's the full range of your interest. We need to assume that we are interested in representing the signal between plus or minus 5 volts. So that's the full range, plus or minus 5 volts. Okay? So XM is like 5 volts. We need to decide as an engineer, as a kind of architect, 一个架构式哈。As an architect of your system, you want to first define what's the range, what's the dynamic range of our interest using your engineering insight. Okay, if you want to represent what kind of signal, then the range we can assume, you can freely assume that your signal, your range of interest will be in between minus or plus x of the full scale. So that the full scale is plus or minus this range. Define that first. Okay? After defining that, then in the end, by coding your signal, everything can be normalized to the range of -1 or to 1. Okay? So in fact, if you open any audio file in MATLAB, automatically it gives you a sequence of number all in between -1 or +1. If you have worked on your first homework, there's a computer part, right? So you are required to open a music file. But if you just plot your signal, you find everything is in MATLAB is in between -1 and +1. Okay. So anyway, as a system engineer, you want to define the range first. Okay. So after defining that, then things become pretty straightforward. So all the secrets just right there in this figure. Okay. So let's go through this figure slowly. So in this figure, remember x is any number before quantization, and x hat is after quantization. Input, output. Okay? X being the input, out being the x hat equals to q of x, where q stands for quantization, a quantizer, so to speak. If q is a quantizer, then what it does to your signal is this. For every sample, then you see immediately you find that output is a step, kind of a ladder. It's kind of like climbing up a ladder, right? You have different levels. Is that clear? So it's a piecewise constant. But for example, if the signal is 0, then after quantization is still 0. But if the signal is too small, then after quantization it stays 0. That's the meaning. Okay? So if your signal is in between 5 delta divided by 2 and 7 delta divided by 2, then after quantization, in this particular example, then after quantization, the output becomes 3 delta. So this is nothing but rounding to the nearest level. 它只是一个四舍五入而已 Chinese. Okay, so it's nothing but rounding to the nearest level. Okay? And here, a bit more detail. Here we intend to do a 3-bit encoding. Okay? 3 bits means 8 level. 3 bits means 8 level. Right? Because you have 3 bits, you have 8 different numbers. Right? So 3 bits means 2 to the 3rd power, or the 3次方 8 levels. So that's the idea. Okay? That's the idea. So this figure is showing us an example where we have a rounding operation, 四舍五入, nothing but rounding, and we have 8 levels which enable us to create 3-bit representations for each number. Okay? Yeah. So far so good. Does it make sense? It's just rounding to the nearest level. But now we need to talk about our notation. Okay, so here delta has a name of step size. Step. Each step is 1 delta, 2 delta, 3 delta step size. Going up by 1 step, going down by 1 step, minus delta, minus 2 delta, minus 4 delta. 8 different levels. And as I previously mentioned, plus or minus m is, you can say that, you can refer to it as the full scale. Okay? In this case, I will say, okay, assuming that the full scale is plus or minus that. Full scale, step size. And then as a simple matter of fact, then we have what's the relation between delta and full scale? What's the relation between delta and full scale? So the relation is, let me just write down. Okay? Now the relation is delta equals to full scale 2xm divided by 2 to the number of bits. Okay? That's a relation. Here, this thing is number of bits. Because the full range is from minus to plus xm, right? So this range is 2 times xm, and then we have 3 bits. So in this case, 2xm, the full range, divided by 2 to the third power, which is 8. So that leads us to delta equals to what? That. So that's a very simple matter of fact. We do have 8 levels right here. So we are going from minus 4 delta to 3 delta, and this is our convention. This is our convention. Okay? Delta, the step size equals to the full range equally divided by 2 to the number of bits, okay? Which is equal to 8. 是8等于8 in this example. So far, so good? Is it making sense? It's very simple, very straightforward. Just take a look at this figure as an example. But then, the next thing we want to pay attention is right here. So now we have 8 levels. It remains to be determined how we represent these 8 levels using 3 bits. How exactly are we going to do that? So the coding scheme. So there are different coding schemes, different methods for coding, for putting the levels, for naming the levels by 3 digits, by 3 binary digits. So here is one example. In one example, that's called 2's complement. So in this coding scheme, we represent 0 by 0, 0, 0. That's very straightforward. And of course, we represent 1 delta. We represent this level by 0, 0, 1. And we represent 2 by 2, 3 by 3, right? That's just basically the binary representation for the positive integers. You can do that. But then, at the negative value side, 2's complement scheme goes this way, okay? It's 0, 1, 2, 3. And then what happened to 4? 4 becomes down there. That's 2's complement. Let's take a look at this together one more time. Okay, ready? 0, 1, 2, 3, and 4 down there, representing the most negative value. And then 5, 6, 7. 6, 7. 6, 7. So that's the way. That's 2's complement code. Okay, it's just a traditional way. And what's cool about this? And this other way we are not going to emphasize. Okay, this other way is more straightforward. It's just shifting. Shifting by an offset, just redefining the most negative as 0. So that's more straightforward. But 2's complement is cool in that now you can tell if the value is negative or positive by simply looking at the first bit, the most significant bit, right? This is a sign bit. Sign 1, right? That's negative. 1 is negative, 0 is positive. Okay, that's a good convention. Right. So even if after we decide how to round your signal to the nearest level, still it remains to be discussed. You can determine which scheme to use. Do you want to use 2's complement? Do you want to offset? Okay, both are okay. Right. But 3 bits leads to 8 levels, and so on and so forth. So far, so good? Yeah? All right, so now an exercise before we leave. Now, if our full scale, in this example, if our full scale is plus or minus 1.6 volts, and I have a binary representation, 8-bit representation, then what does this code represent? Which level does this code represent? Let's work it out. Okay, I give you maybe 2 minutes. Let's try to work this out. And just for your reference, this is a figure for 3-bit representation, but now we have 8 bits. What will this code represent? Right? Okay, so all right. So maybe tomorrow we come back and check on. Oh, no, not tomorrow. Next week when we come back, we check on that. Okay. So basically, you get an idea how maybe you want to calculate this. It's doable, right? Yeah. So the next slide. Okay. Next slide is an important concept, and I can probably stop here or maybe one more slide, something like that. So here I want to just share with you important concept. Okay, this is quite important. So let's take a look. So on the left, you have this good old figure showing what's happening when you quantize a signal using 3 bits. Yeah. The I/O function is looks like a ladder, 看起来像个楼梯. Yeah. And we call it Q of x. Okay. So schematically, we say input on the left, output on the right. So x after quantizer, what it does to your signal is this is a function. Okay. So x hat is a function of your input, and it's being changed by the being quantized. Yeah. Quantizer is a function. Is this function? Okay. Q of x. Q of x represents a quantizer, but a lot of times we need to think in a different way. Okay. And that's an important concept I want to communicate to you. In most of the time, somehow it's more convenient to think of quantization as if it introduces an error. Let me repeat that, okay? It's more convenient a lot of times to think of quantization as if it introduces an error. And what's the error? Error, of course, is the difference, right? So we say that after quantization, your signal is superposed with an error. Error signal, E of n, error signal. It's really a concept. And that will be further developed, okay? So can you force yourself to think this way? Quantization introduces an error signal, okay? In that your signal, original signal is the result after quantization plus, I'm sorry, the other way around. Quantization is a result of your signal plus an error. The sign is plus right here, okay? So this, as I said, it's an important concept in that we approximate quantization as if it's your signal plus a noise term. Later, we'll try to convince you that this error looks like noise. Okay? And that's not the most straightforward thing to understand. Okay? So I want to take it slowly to make sure that it's clear to everybody what I intend to tell you. My intention is this. We approximate x as if it's the original signal plus a noise term or error term, noise term. Because your error turns out, as later we'll see, your error looks like noise. Okay, and that's not the most straightforward thing to understand. Okay, yeah. Okay, so maybe if keep watching the next slide. So in next week when we come back, I'll go through these slides. So we'll have an example of a sinusoid, okay, a sine wave, and after quantization, it looks like that. Okay, after quantization, 3 bits, 8 levels. That's the result. And this is the result. So then you can just calculate the difference and call it the error signal. Yeah. So the next slide, the error signal looks like this. This is after quantization. You can kind of recognize this may be a sine wave if you just look at this. And because there's so much error being introduced after quantization, okay? Error signal. And this is using 3 bits, and that's an example of using 8 bits. 8-bit, 3 bits. Yeah. So later, when we come back next week, we'll see that when we increase the number of bits to 16, 8 or 16, it turns out that if you just observe the distribution of quantization error, it looks like uniform distribution. It will look like uniform distribution. So then, voila, we can model noise as a random variable. Okay, so usually the good part is that noise, when we say noise, that means we model it as a random variable. So probability comes in this course, in this context. Okay, by quantization, 四舍五简单嘛, right? But turns out it can be further developed into probability. Okay, so quantization noise very conveniently regarded as a random variable in that its distribution is almost uniform, approximately uniform, right? So later we can even discuss what do we mean noise? Yeah, property of noise. There are a few. Noise can be stationary noise. Noise is uncorrelated with the signal, or the noise is even white. White noise. Okay, so we'll get to these points next week when we come back, and later we can even just do simulation. We can simulate what if we have 3 bits, 7 bits, 11 bits, or 15 bits. Then what's the power spectrum? Does it look white? So in this figure, on horizontal axis, that's the frequency. Okay, if you have a flat spectrum, that basically means that your signal is white, your noise is white. Okay, so what will happen? It turns out that probably you do need to create the more bits, the better. You want to enhance your resolution so that your quantization noise become white. Okay, so such kind of things are what can be developed next week when we come back. And for tomorrow, please, for those of you that are willing to share what you have for homework 1, please remember to sign up. Or is the sign up TA? Is the sign up still? Can they still sign up? Yeah. Okay. So you please just check with the TA previously sent a message, right? There's a link for signing up for tomorrow's discussion. So with that, I'd like to thank you for being here today. I'll see you tomorrow.